Welcome! In this session, we'll be tackling an exciting problem from LeetCode, problem number 1505, titled Minimum Possible Integer After at Most K Adjacent Swaps on Digits. Together, we'll explore the challenge, break it down, and analyze approaches to solve it effectively. Let's dive in. In this problem, you are given a string number that represents a large integer, and an integer k that specifies the maximum number of adjacent swaps you can make between digits of number. Your task is to determine the smallest possible integer, in lexicographical order, that can be formed after performing at most k swaps. The input includes the string number, which can have a length between 1 and 40, and the integer k, which can range from 0 to 10 to the power of 9. The output should be a string that represents this minimum integer. This means you're optimizing the order of digits by carefully choosing adjacent swaps, while staying within the allowed k moves. For example, in the first case, if number is 4321 and k is 4, the goal is to make the smallest number possible by performing up to 4 adjacent swaps. To achieve this, we can perform the following sequence of swaps. First, swap the first two digits to get 3421. Then, swap the first two digits again to get 3241. Next, swap the second and third digits to make 3214, and finally, swap the last two digits to get 1342. After exactly 4 swaps, the minimum number we can form is 1342. This demonstrates how careful planning of swaps can achieve the smallest possible result within the given limit of k moves. In another example, if number is 100 and k is 1, we can only perform one adjacent swap. Swapping the first and second digits transforms 100 into 010, which is the smallest possible integer in this case. Since no additional swaps are allowed, the result remains 010. On the other hand, if the input is 36789 with k equal to 1000, the number is already in its smallest lexicographical order. Here, no swaps are needed, even though k is large. The result is simply 36,789. These examples highlight how the constraints of k and the initial arrangement of digits impact the solution. The constraints of the problem clarify that the length of number is between 1 and 40, and number consists only of digits from 0 to 9. The value of k can range from 0 to 10 to the power of 9, which means you must account for cases where swaps are effectively unlimited for shorter strings. The goal is always to minimize the integer by arranging digits in the smallest lexicographical order. Key considerations include prioritizing the smallest digits for leftmost positions and handling edge cases, such as when k equals 0, meaning no swaps are allowed, or when the number is already in its minimal order. Additionally, pay attention to scenarios where swaps create leading zeros, as these can affect the result and must be handled correctly. When approaching LeetCode problem number 1505, it's important to consider a range of strategies to identify the most efficient solution. The brute force approach, for example, involves exploring all possible permutations of the string number that can be formed with up to k adjacent swaps. While this guarantees the correct result by exhaustively searching every possible solution, the computational cost is immense. The factorial growth of permutations, even with pruning, makes this approach impractical for larger inputs. Another option is a greedy approach using a sliding window technique. Here, the idea is to iteratively find the smallest possible digit for each position by searching within the next k positions. This method is more efficient than brute force, as it constructs the minimal number step by step. However, its reliance on linear searches within the k range still leads to inefficiencies for larger values of k, as the complexity scales with both n and k. To further optimize the solution, we can use a more advanced approach that leverages data structures like a segment tree or Fenwick tree. These allow us to efficiently identify the smallest digit within the next k positions and maintain quick access to indices for updates. By doing so, we improve the greedy approach, reducing the time complexity of finding the minimal digit to logarithmic time. Building the data structure requires O, n log n, and each query or operation also takes O, log n, making this method highly efficient. This approach not only ensures correctness by always finding the minimal solution but also scales effectively with larger problem sizes, making it the most suitable strategy for the given constraints. The optimized approach using a segment tree or similar indexed data structure was selected due to its ability to balance efficiency and correctness. The problem fundamentally involves identifying the smallest digit within a limited range, which is why a logarithmic time query mechanism is invaluable. By iteratively and greedily processing the digits, we can construct the minimal number incrementally while performing the fewest swaps necessary. This strategy effectively handles larger inputs while maintaining accuracy. The key insight here was recognizing that the problem could be reduced to efficient range queries and updates, which advanced data structures are specifically designed to handle. This realization was the turning point in identifying the most scalable solution. When comparing the approaches, the trade-offs become clear. Brute force guarantees correctness but is far too slow to be practical. The greedy sliding window strategy improves on this by reducing the complexity, but it still suffers from inefficiencies due to linear searches within the K range. The optimized approach with advanced data structures, on the other hand, provides the best balance between correctness and efficiency. By leveraging logarithmic time operations, it scales effectively with larger inputs while adhering to the constraints of the problem. This combination of accuracy and performance makes it the ideal solution for tackling problem number 1505. In this problem, the objective is to find the smallest possible integer by performing at most k adjacent swaps on the digits of the given number. For example, if the number is represented as a string like 4321 and we are allowed 4 swaps, we need to carefully plan our operations to achieve the smallest possible arrangement of digits. However, it's important to note that directly sorting the digits isn't valid unless the swaps required to achieve that order are within the limit of k. This makes the problem non-trivial and requires a strategic approach. To solve it efficiently, we use a greedy strategy combined with a Fenwick tree, which allows us to manage the swaps and calculate the number of inversions efficiently. Let's break down the algorithm step by step, starting with understanding the constraints of the problem. Now, the first step in solving this problem is to make a greedy choice for selecting the minimum digit. To do this, we start scanning the string from left to right. At each position, we determine the smallest digit that can be swapped to the current position, but only if it lies within the range permitted by the k-swaps. This ensures that we're always making the optimal choice for minimizing the number at each step. To efficiently calculate the cost of each swap and keep track of the positions of the digits, we use a Fenwick tree. This data structure is key to ensuring that our solution is efficient. It helps us dynamically track the number of swaps needed as digits are moved and ensures that updates to the positions of digits are handled efficiently during each iteration. Let's see how this Fenwick tree is utilized in greater detail. Next, we perform the swaps iteratively. For each position in the string, we identify the smallest digit within the range allowed by the remaining number of swaps. To do this, we calculate how many swaps would be required to bring each candidate digit to the current position. If a candidate digit requires fewer swaps than the remaining k, we select it, update the value of k by subtracting the swaps used, and proceed. The Fenwick tree is updated dynamically to reflect the changes in positions after each swap. This ensures that the cost of subsequent swaps is calculated correctly. Once the swap is executed, we move to the next position and repeat the process. The algorithm continues until all positions are processed or there are no swaps left to perform. At this point, the string represents the smallest number that could be achieved within the given constraints. The key insights behind this algorithm are rooted in the greedy approach and the efficiency of the Fenwick tree. The greedy strategy ensures that we always prioritize bringing the smallest possible digit to the current position, as long as it's feasible within the allowed number of swaps. Without the Fenwick tree, calculating the cost of each swap would require iterating over the entire string, resulting in a time complexity of O(n squared). However, the Fenwick tree reduces this to O log n for each update and query, enabling the overall algorithm to run in O(n log n). Additionally, we can terminate the algorithm early if k reaches 0, saving unnecessary computations. The Fenwick tree dynamically tracks the number of digits that need to be jumped over during swaps, while a priority queue can optionally be used to efficiently retrieve the smallest digit within the allowed range. Together, these components enable an optimal and scalable solution. Finally, let's consider some edge cases and analyze the complexity of the algorithm. If the input string consists of a single digit, no swaps are possible, and the output is simply the input itself. When k is large enough to allow a full sorting of the digits, the result is just the sorted string. On the other hand, when k is very small, the algorithm must carefully select swaps to maximize their impact on minimizing the number. Duplicate digits are handled naturally by considering their positions within the string. In terms of complexity, the time requirement is O, n log n, where n is the length of the string, due to the Fenwick tree operations. The space complexity is O, n, to store the tree and auxiliary structures. For example, given the input 4321 with k equals 4, the smallest digit within 4 swaps is 1, which is swapped with 4 to yield 1324. After one more swap, we obtain 1234, which is the output as no further swaps are possible. This example demonstrates the efficiency and correctness of the algorithm. This code defines a function min_integer that finds the smallest integer possible from the input string number after performing at most k adjacent swaps. The solution employs a greedy strategy combined with the use of a sorted list from the sorted containers module to efficiently manage indices and calculate the number of swaps required to move the smallest digit to its desired position. 1. Initialization. The available list keeps track of the indices of the digits in number. The sorted list ensures efficient operations like insertion, deletion, and binary search. 2. With greedy selection. For each position in the result, we iterate through the indices in available to find the smallest digit that can be moved to the current position with at most k swaps. 3. Counting swaps. Using sorted list s bisect _ left, we calculate the number of swaps needed to move a digit by determining how many elements are before it in the current order. If the swaps are within the limit k, the digit is added to the result. For update state, after choosing a digit, we update k, subtracting the swaps used, remove the used index from available, and continue until all digits are processed. This approach ensures an efficient way to determine the result while adhering to the constraints of the problem. Here, we begin with the Java implementation of the solution. First, we import the necessary packages, including java.util*, which provides the utility classes we need for this approach. Inside the solution class, we define the min_integer method, which takes the input string number and an integer k, the maximum number of adjacent swaps allowed. The length of the string is stored in n, and we initialize a string builder called result to construct the final answer. Additionally, we use a tree set integer named available to keep track of the indices of the digits in the input string. The tree set is particularly useful here because it provides efficient operations to retrieve and manage sorted indices. Next, we populate the tree set with all indices of the string number using a simple loop from 0 to n1. This ensures that all positions of the digits are initially available for processing. Then, we move into the main logic, where we iterate n times to build the result string digit by digit. Inside this loop, we use an iterator to traverse through the indices in available. For each index, we calculate the number of swaps required to bring the digit at that index to the current position in the result. This calculation is done by subtracting the size of the headset, a subset of indices smaller than the current index, from the index itself. If the swaps required are less than or equal to the remaining allowed swaps k, we append the digit at that index to the result, update k by subtracting the swaps used, and remove the index from the tree set, as it's no longer available for further processing. Finally, the loop continues until all digits have been processed, and the result string contains the lexicographically smallest number possible after at most k adjacent swaps. The method then returns result.toString, which converts the string builder into a string. The use of a tree set ensures that the indices are always processed in sorted order, and the iterator allows us to efficiently calculate the swaps required for each digit. This combination of data structures and logic ensures that the implementation is efficient, even for larger input sizes. The solution carefully balances the constraints of the problem while optimizing for performance and clarity in the code. To solve this problem, we start with the number 4321 and aim to make it as small as possible using at most 4 adjacent swaps. First, we initialize our variables, the number itself, the maximum allowed swaps, and some helper structures. The result list will store the digits of our final number as we build it, and available is a sorted list of indices representing the positions of the digits we can still work with. In the first iteration of the outer loop, we evaluate which digit can be moved to the first position with the fewest swaps. The inner loop considers each index in available. For the first digit, we check index 0, which requires 0 swaps since it's already at the beginning. We add the digit 4 to our result, remove its index from available, and update our state. At this point, the result contains 4, the available indices are 1, 2, 3, and we still have all 4 swaps remaining since none were used. Now, we continue building the result with the next iterations of the outer loop. For the second digit, we again evaluate the smallest possible value from the available indices. This time, we check index 1, representing the digit 3. Since no swaps are needed to place 3 in the next position, we append it to the result and remove its index from the available list. Our result is now 4, 3, the available indices are 2, 3, and we still have 4 swaps left. Repeating this process for the remaining digits, we append 2 and 1 to the result one by one, as each is already in its correct position without requiring swaps. By the end, the result list contains 4, 3, 2, 1, and all indices in available have been used. Since no swaps were necessary, the final output remains 4,321. In the second example, we work with the number 9,876 and are allowed only one swap. We initialize our variables similarly, with the result list starting empty and available containing all the digit indices. In the first iteration of the outer loop, we evaluate which digit can be placed in the first position. Starting with index 0, we find that the digit 9 is already in the optimal position, requiring 0 swaps. We append 9 to the result and remove its index from available. The result is now 9, and the remaining indices are 1, 2, 3. For the subsequent iterations, since we're working with a single swap and no better arrangement is possible, the remaining digits 8, 7, and 6 are simply appended to the result in their current order. Thus, our final result is 9, 8, 7, 6, and the output is 9,876. Now let's consider the third example, where the number is 2,341 and we have up to 2 swaps available. As before, we initialize our variables with an empty result list and available containing all indices. In the first iteration of the outer loop, we evaluate the smallest digit that can be moved to the first position. Checking index 0, we find the digit 2 is already the smallest and in the correct position, requiring 0 swaps. We append 2 to the result, remove its index from available, and move to the next iteration. The result is now 2, and the remaining indices are 1, 2, 3. In the second iteration, we again check the smallest digit that can be placed next. Index 1 represents the digit 3, which also requires 0 swaps to remain in its current position. We append 3 to the result, remove its index, and update our state. At this point, the result is 2, 3, and the remaining indices are 2, 3. In the third iteration, we repeat the process to find the smallest available digit for the next position. Checking index 2, we find the digit 4, which is already where it needs to be, so we append it to the result without using any swaps. The result now contains 2, 3, 4, and the remaining indexes, 3. Finally, with only one digit left, we append 1 to complete the result. At this stage, all digits have been used, and the result list is 2, 3, 4, 1. After converting this list back into a string, the final output is 1234, which is the smallest possible integer we can achieve with at most 2 swaps. The time complexity of the solution arises from multiple nested operations, and we can analyze each part individually. First, the outer loop iterates over the digits of the string number. Since the loop runs once for each digit, and the result list grows by 1 digit per iteration, this contributes O(n) to the overall complexity. Next, within the outer loop, there's an inner loop that iterates over the available indices. Initially, the available list contains all n indices, but it shrinks by 1 index after each iteration. This means that in the worst case, the inner loop runs n times for the first digit, and 1 times for the second, and so on, resulting in a summation of n plus n1 plus n2 plus 1. This summation simplifies to O(n) squared. Additionally, the bisect_left operation, which is part of the sorted list library, is used to calculate the position of a digit. Since it relies on binary search, it has a time complexity of O log n. Finally, removing an element from the sorted list also takes O log n. These operations combine to determine the total time complexity of the solution. Given that the inner loop runs n squared times in each operation within it, such as bisect underscore left in pop, takes log n, the overall time complexity becomes n squared asterisk log n. Shifting focus to space complexity, the solution uses additional memory for various data structures. The result list, which stores the final permutation of digits, grows to a maximum size of n, contributing n to space usage. Similarly, the available list, implemented as a sorted list, initially holds n elements and decreases in size as indices are removed. Internally, the sorted list uses balanced binary trees, which also require n space. Besides these, other variables like number, k, idx, and swaps use constant space, which is 1. When we sum up these contributions, the total space complexity of the solution is n. To better understand the efficiency of the solution, let's compare it to a brute force approach. A naive method would involve generating all possible permutations of the digits and checking each one to find the smallest valid number after at most k-swaps. Generating these permutations would take n time, which becomes infeasible for larger inputs. In contrast, the optimized solution leverages the sorted list data structure to efficiently manage and query indices. The use of binary search for the bisect underscore left operation and logarithmic time for removal ensures a significant reduction in complexity compared to manual iteration. When analyzing different cases, we find that in the best case scenario, such as when k is very small or the input number is already sorted, the inner loop terminates early, and the dominant complexity is n asterisk log n. However, in the average and worst cases, the nested loops and operations on the sorted list lead to a time complexity of n squared asterisk log n. To mathematically validate the time complexity, consider that the outer loop runs n times, contributing n. On average, the inner loop executes approximately n/2 iterations, with each step involving log n operations for binary search and removal. This results in a total complexity of n squared asterisk log n, which dominates the other terms. In summary, the solution achieves significant improvements over brute force by utilizing efficient data structures like sorted list to minimize redundant computations. Despite its nested loops and logarithmic operations, the solution is much faster and more practical than naive methods. The final time complexity is n squared asterisk log n, and the space complexity is n, making the algorithm efficient yet manageable for real-world inputs. One common mistake when solving this problem is to make greedy choices without fully accounting for the constraints of the k-swaps. For example, if you always pick the smallest digit at each step but ignore how far the digit is from its current position, you might end up using more swaps than allowed, rendering the solution invalid. To prevent this, you can use data structures like a Fenwick tree or segment tree. These structures help you efficiently calculate the minimum number of swaps required to move a digit to a specific position. Another frequent issue is attempting a brute force implementation, where you try every possible permutation of k-swaps. This approach quickly becomes computationally infeasible, especially for larger inputs, since its factorial time complexity grows exponentially. Instead, focus on a greedy strategy combined with efficient data structures to reduce unnecessary computations. Finally, edge cases can be overlooked, such as when k equals 0 and no swaps are allowed, or when the digits are already in ascending order. Testing these scenarios is crucial to verify your solution's robustness. Another challenge arises from mismanaging data structures. Using a simple array instead of a more advanced structure like a Fenwick tree can lead to inefficiencies, especially when performing frequent range queries or updates. Fenwick trees and segment trees are particularly well suited here because they allow you to handle these operations in log n time. Additionally, when implementing sorting logic, failing to maintain the relative order of digits can lead to errors. This is especially important when multiple digits are tied in value and their positions matter. To avoid this, ensure that your sorting algorithm respects the original ordering within the constraints of the k-swaps. These considerations are critical for writing an efficient and correct solution. From an interview perspective, this problem is often used to evaluate your ability to combine a greedy algorithm with advanced data structures. It's not just about deriving the solution but also about demonstrating your thought process. You should be prepared to explain how you break down the problem, identify bottlenecks, and use tools like Fenwick trees or segment trees to optimize performance. A key insight here is understanding why a greedy approach works and how these data structures enable efficient range queries, which are essential for minimizing swaps. Interviewers might also ask you to discuss trade-offs between different approaches, such as the brute force method, a purely greedy strategy, and a hybrid approach that incorporates data structures. Finally, it's important to clearly articulate the time and space complexity of your solution. For example, the optimal approach here typically has a complexity of n log n, which balances efficiency with implementation complexity. This problem shares similarities with other LeetCode problems, making them valuable practice for honing the necessary skills. For instance, LeetCode number 321, create maximum number, also requires selecting digits strategically to form the largest possible number, often using greedy techniques. LeetCode number 1675, minimize deviation in array, focuses on minimizing a value, leveraging efficient data structures like heaps, which parallels the need for optimization here. Another related problem is LeetCode number 406, queue reconstruction by height, where sorting and greedy choices are used to achieve a specific arrangement. Finally, LeetCode number 164, maximum gap, emphasizes efficient calculations over gaps or distances, which aligns with the need to efficiently manage digit positions within constraints. Exploring these problems can deepen your understanding of the concepts and methods relevant to this challenge. There are several approaches to solving this problem, each with its own trade-offs. A brute force method would involve trying all possible permutations of k-swaps. While conceptually straightforward, this approach has exponential time complexity, n, making it impractical for larger inputs. A simpler alternative is a greedy approach without additional data structures, where you iteratively choose the smallest digit within the allowed range of k-swaps. While easier to implement, this method can become inefficient for larger values of n due to repeated scanning of the digits. The most optimal approach combines a greedy strategy with data structures like Fenwick trees or segment trees. These structures allow you to efficiently find and swap the smallest digit within the allowed range, achieving a time complexity of n log n. However, this method is more complex to implement and requires a solid understanding of these advanced data structures. Each approach has its merits and drawbacks, so understanding their trade-offs is key to mastering this problem. Thank you for watching. We've covered a lot in this session, including approaches to solve LeetCode problem number 1505, the importance of greedy algorithms, and how to optimize solutions under constraints. Keep practicing to sharpen your skills, and don't forget to check out our other tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!